Hey, hi, I'm Dave Dugan. I'm the president of EBTRON. I'm out here in Paso Robles today. I'm at Halter Ranch Winery in the caves, actually behind the winery. It's kind of cool back here. So, any rate, what we're going to do today is we're going to have a presentation on demand control ventilation. I'm not going to do it from here. And then we're going to, at the end of it, we're going to switch a lot of you over that want to join us to go to meeting instead of go to webinar. And we do that because that's kind of more interactive at the end. And winemaker Kevin's house is going to be on. He's a great guy. We've done this before with him. He'll be here out here in the caves. And I hope you enjoy it. I hope you participate with us. I've got a couple of little surprises, I think, today. But at any rate, this is our holiday virtual, and but this year I'm doing a little more of a specific topic than I have in the past. It's not nearly as general. So I'm going to go get out of this jacket and just go right next door and get into a space that's a little more comfortable to give this presentation. Okay, so it's really literally right next to me. So I'll be right back. See ya. Okay, one of my surprises, I guess, today, and hopefully this works out. I really haven't done anything like this before. We're going to do it. We're going to call it our holiday participation game. And there's actually a couple reasons I do this. One is I like to give things away, and the other is I like to find out how many of you actually pay attention and listen to this thing. So basically what we're going to do is we're going to have a game. It's only, for the guests, not for the reps, obviously not for EBTRON or ESC people or anybody like that. But for those of you that are guests that are registered and are in the state where we can legally ship you wine to, we're going to let you play a game as you go along. So you might want to have a pen or pencil and a little piece of paper that you can use to mark off these little wine glasses, and they're going to show up on a number of slides, and basically when you see one, just count it, and at the end we're going to give you like a little 15-minute window. We don't want to give you too much time because we don't want you talking to other people. So between 4 and 4:15 p.m. Eastern time, so whatever time zone you're in, just add, just subtract from that, okay? And email to askdave@engineeredsalescorp.com how many wine glasses you actually counted. Don't include this one that is on this slide, okay? And only one, entry per registered guest. And we're going to total it up tomorrow. We're not going to total it up today. And then all of you that participated, we'll send you an email, say either you won or you didn't. I'm going to assume that there's going to be quite a few of you that have, there's a lot of people on this, so I'm going to assume there's quite a few of you that will come up with the right answer. So of those of you that have the right number of wine glasses, we're going to do a random pull. Okay, so again, the way this works is just count those wine glasses on the top right of the slide when you see it, not including this one, and email your total to us. Don't worry about your address or anything like that. We don't need it yet. We'll contact you back if you won and said, hey, where do you want us to ship this? And again, it has to be in a state that we can ship to. All right, so hopefully somebody enjoys that. Walter's got some great wine, and I'm going to pick the case out at the that we're going to ship. Okay, thanks. Okay, we're going to do this presentation on demand control ventilation. It's a pretty specific presentation for me. We're going to talk about DCV strategies to improve IAQ and save energy. Okay, so how is this going to go about today? Well, we're going to have some breaks in here. I mean, it is the holidays, and I am at a winery, so I'm here with my wife, so I plan to take a few breaks. But basically, the way this is going to go down is we're going to talk about ventilation for acceptable indoor air quality. I do this quite a bit, so that's not necessarily going to be new to a lot of you, but if you've listened to me before. But IAQ fundamentals, and then what affects outside air intake flow rates. It's very important, whether you're doing demand control ventilation or you're not doing demand control, or you're just doing like fixed set point ventilation. There's a lot of things that affect outdoor air and how much outdoor air comes into your mechanical equipment. So we're going to want to go over that. And then once we go through that, we're going to go into demand control ventilation. We're going to talk about the definition of DCV from ASHRAE's perspective and what true compliance would be. And then we're going to talk about CO2 and ventilation. CO2 seems to be the most common way folks are doing demand control ventilation, but when you see what the definition of it is, you're going to say, well, that's not the only way to do it. And there's a lot of problems with CO2 and ventilation, and particularly CO2 DCV. So we're going to discuss improving CO2 DCV, and then talk briefly about an alternate way of doing it, population-based DCV, a couple different ways to do it. And once we get through that, we're just going to touch on airflow measurement technologies, primarily the EBTRON technologies. I don't want to spend a whole lot of time on other technologies today. And then when we get into control strategies, again, that's going to be kind of like a fast version. It's more going to be a bunch of schematic slides that we're going to look at and just give you an idea of what we need to do. We're not going to dig into actual detailed sequences, but we could come back and do that at another time, okay? So we're going to start with ventilation for acceptable IAQ. Okay, so fundamentally, the fundamentals, what are the fundamentals? Well, when we talk about indoor air quality, quite honestly, dilution, ventilation, or outdoor air, it's paramount to IAQ, okay? And when we look at ASHRAE standards, our standards today, we're just really we're not really talking about healthcare facilities, but if we were, we'd have a very similar conversation about the importance of outdoor air for dilution ventilation. But today we're going to really more say, hey, standard 62 and the IGCC, which is based on standard 189, standard 241, they all have a very significant component about outdoor air ventilation and dilution, of using outdoor air. And the reality of it is outdoor air is pretty, it's an energy hog, okay? So at least when we're in a what we call minimum outdoor air mode, meaning we're not free cooling, okay? So it's an energy hog. We're not going to get into it today because it's not really part of this discussion, but if we were going into a little more detail about indoor air quality, we would be stressing that it's, you got to be careful about how much contaminants you transport into the building before it crosses a filter or a coil. And when you get into the more humid climates east of the Rockies, whether down to the Gulf and all the way up into Canada, it's still, there's a lot of moisture that we have to deal with, and that's a problem. But that's not really what we're doing today. Okay, so what we need to do is, I think this is important when you have a DCV conversation, especially for those of you that are relying solely on CO2 for DCV, okay? Because we have a lot of contaminants we have to concern ourselves with. It's not all occupant generated, all right? So we have VOCs, we could have other chemicals, but that's on the building generated side. On the biological side, basically there, I'm driving that towards, moisture driven problems. So building envelope issues are generally pressurization issues where we're bringing moisture from outdoors, indoors. Intake plenum, supplier plenums is more of a flow rate problem where we have water carryover problems, whether it be water carryover off of coils or water carryover into an intake unit. So again, they have not really anything to do with the occupant component, okay? And outdoor generated via HVAC system, it could be just poor quality outdoor air, but really I'm even just saying here a little more general. It's like, hey, we have some really bad maintenance out there, and filters and filter integrity kind of gets, kind of overlooked a lot. The through doors and across the building envelope, again, are pressure related. Okay, and then finally we have occupant generated body odor, which is when you're doing CO2 based DCV, that's really all you're focusing on. I've had a problem with that for a long time. It's like, okay, yeah, occupant generated's a big deal, particularly in, high occupant density spaces, but we have all these other things we have to worry about, and simply measuring carbon dioxide isn't going to tell us everything we need to know about the other contaminants. And then, of course, we have to deal with the fact that, in 2020, we had COVID-19, so airborne pathogens, that changes things up a lot too, okay? So that's pretty much where we're at, in terms of understanding the contaminants of concern. It's pretty simple, but I like to do this. It's like if we look at an occupied zone or space, and we had no outdoor air coming into it for dilution or no filtration that could remove the contaminants of concern, what would happen is the contaminants would build up and we'd eventually have a problem, okay? And I remind everybody that that's exactly what happened during COVID when people went home, because we really didn't have any outdoor air for dilution, most of our residences, and we still really don't. And we're, the filtration in the residences, if we pulled out the dog hair, we did good, okay? So, people would go home, we'd have more problems. But listen, the truth of the matter is operationally, a lot of our buildings are inadequate ventilation, inadequate filtration. And so what we want to do is, we want to at least do the basic fundamentals, which is bring in outdoor air for dilution and have targeted high-level filtration that removes whatever it is we're concerned with. Now, some of you say, I'm doing some other things for filtration. That's great, but that should be in addition to, or I'm doing UV lights or something like that to kill viruses. That's great, but this is still the fundamentals, okay? So let's not forget the fundamentals here, all right? Standard 62 specifies outdoor air ventilation rates. I was somewhat disappointed that the title changed. It used to say ventilation for acceptable indoor air quality, because I think that's where the focus was. Now it says ventilation and acceptable indoor air quality. And quite honestly, those of you that are really on the energy side of life are what's driving that. But let's not forget, we have energy standards. ASHRAE is 90.1 for energy, and that's great. We have to do that. But if we have the ventilation standard all of a sudden be driven by energy and not driven by, occupant health and well-being, we're going to have a big problem. We're going to have a bigger problem than we had the last time. Okay? And believe me, I've been around a long time. I've seen this happen. I've seen this cycle through over the years. Regardless, today your codes are driven on ventilation rates. It doesn't matter to me if you're in the IMC or the UMC. And even those of you in California, there are some types of facilities that are really driven by the UMC, okay? All of those codes are standard 62 based. Now you might be somewhere else. You can't really see that map, but the brown areas are on that map are not necessarily IMC or UMC. But in a lot of cases, they really are driven off of those. And those are all standard 62 based ventilation rate procedure, really, in terms of rates. And so that's most of the United States. Now I have people on here from outside the United States, but that's what I got. And then when you get into California, you got the energy code. So when you're in California and you have to deal with the UMC, that's basically Title 24 Part 4. But most of you think about Title 24 Part 6, which is the energy code. And really, it doesn't matter. They're all rate-based. When you look at Standard 62, actually, Standard 62's ventilation rates for most spaces are less than that of Title 24, Part 6. if I'm actually more of a fan of Title 24 Part 6's ventilation requirements, of pretty much straight 15 CFM per person, where Standard 62 kind of gets all over the place, and honestly, in some types of spaces, the ventilation rates, in my opinion, are way too low. But that's basically what we have to deal with there. And when it comes down to outdoor air intakes, okay, you just can't, you just don't set it and forget it. All right, and it's, I'm going to focus a lot on recirculating units, but DOAS systems have similar problems, but not identical, okay? But you just can't set it and forget it, particularly if it's multi-zone DOAS systems, okay? And especially if they're doing DCV, okay? So, what are the things that affect this? Well, it's fan speed changes, which most people seem to understand that. But wind and stack pressure, most people seem to ignore. It's like, hey, we have this thing called the wind that blows on a building and blows on an intake, and we have changes in temperatures. And that all results in changes in pressure across the intake, which, depending on how you're controlling or not controlling your outdoor airflow rates, is going to affect how much air comes into that unit. Okay, and then if you are using dampers, particularly recirculating units here, using dampers, but you could be, even though I'm looking at dampers here at the unit, we could be relying on damper position, say on DOAS at the zone level. It's like, listen, there's a lot of problems with dampers, okay? And in terms of problems, they're just not regulating valves, okay? So we're gonna have to look at all that. And basically, when you look at this, we see that outdoor air intake flow rates on uncontrolled outdoor air on various systems will vary by more than 50% of whatever your desired set point. So, you should ask yourself, well, why is that? Okay, and so when we go and look at this, it kind of dates me and a few other people, but this paper was published in January of 1990 because in 1989 Standard 62 recognized that the energy folks went a little overboard with reducing outdoor airflow rates in the 70s and the 80s because of the 70s energy crisis. And in 1989, Standard 62 made a major change in ventilation rates, much higher than we are today, okay? In fact, even higher than Title 24 Part 6. And so, we knew there were problems, we knew there were air quality problems, and we needed to get people to understand that they just couldn't set it and forget it, which is what they were doing, which is what we're still doing a lot, okay? And so this paper was written by Solberg, myself, and Damiano, but really mostly by David Solberg was the primary author here. He did a great job on this paper. I always tell people, if you ever meet Dave, he's always way ahead of his time. But anyhow, it's an old paper, but I still use it. And we just basically start off by saying, look, let's look at fan speed changes. The easiest way to look at the problem is we don't put a return fan in. It doesn't mean that this problem doesn't exist when there's a return fan. It just means it's a more complex analysis required, okay? This is very straightforward. We have a supply fan only. There could have been a relief fan, but it's not active, okay? And we have a fixed intake damper, which is pretty common, variable speed system, okay? Well, when you look at that system, what you're saying is that the pressure drop, or I should say the flow coefficient across that louver and damper when it's fixed, or it could have been a hood and a damper when it's fixed, it's a constant flow coefficient. So if I change the mixed air plenum pressure, okay, which is what exactly is going to happen when the supply airflow drops, all right, what's going to happen is the flow is going to drop, and it's going to drop proportionally, okay? And that's exactly what you get here. And most people seem to understand this. That if I have, if I'm looking at a set point at 100% supply and I reduce the supply flow, the outside airflow is going to proportionally track it. And that's just not going to work. It's not the load that, you can have a fully occupied space at peak load and off load and at different supply fan flow rates. Most people think of this as VAV, but really it's not just VAV, it's multi-speed constant volume. It's basically fan coils. It happens on DOAS a little differently, but DOAS to multiple ventilation zones, particularly where we're doing some type of DCV, whether it's true DCV or just occupied, unoccupied modes, okay? But you're gonna have these problems, okay? And that seems to be well understood. You'll see a lot of documentation out there that says, hey, we need to do something about that when we have particularly when we have VAV, poor VAV. Gets kind of bashed when there's a lot of systems that have the same kind of problem. The thing that we don't think about enough is the external pressure variations. And the external pressure variations, what are they? Well, if they change, if the exterior surface pressure goes down, guess what? It's kind of a suction effect on that intake. The outside air is going to go down. And if it was a direct wind, it would go up. Okay, and what causes these external pressure changes? Well, wind pressure is a huge one, okay, and stack pressure is another one, okay. And so wind pressure, I think it should be pretty simple for people to understand. Stack pressure, I mean, it's a little slide, a little picture there, but basically, if you can just imagine that we have an air handler on the roof serving the first floor and only the first floor. Okay, there's a big difference in pressure on that intake system in the winter than there is in the summer. Okay, and really, I don't have good stack pressure data, but I have good wind pressure data because our facility is well instrumented. It's a low rise, so I don't really have stack issues. But what I can show you is, hey, here's a day, system setup, fixed damper, everything else is constant. On a day when there was no wind, we were on that black dashed line for our set point. And on a day when we had a 15-mile-an-hour crosswind, same setup, we had almost a 20% reduction in outdoor air. That's a big deal, okay? And it's going to vary from system to system. And then you see all that scatter in there. And I tell people, look, the scatter is very important for you to understand if you're a controls person. I keep it in there so I only put the scatter for the wind data, which is much worse than the scatter you would see if there was no wind. And it's because if you think about it, on a windy day, you have wind that's blowing down the side of a building, maybe 15 miles an hour, but the next second it's a little bit different direction and maybe 18 or 20 miles an hour, and it just moves around. So dampers can't move quickly enough to compensate for the transient wind gusts, okay? So what we try to explain to controls folks is it's like, listen, when you control outside air, that red line is basically like a 2-minute running average of the data, an integration of the data. Okay, and that's what you want to see, but you want to actually control that scatter, and what that means is you have to really slow down the output of your control loops. If you get the output of your control loops too fast, you end up hunting, and if you try to integrate the raw data coming in, you end up hunting. Okay, and so there's something to be said there. Okay. And then, finally it's like, okay, so you had that black line, which was the fan only effect. And now you kind of, superimpose additional problems like summer stack with a direct wind, which would be the worst case in the example I showed, and winter stack with a crosswind. Your outside air is going to be anywhere between those two red curves. And your set point's that black dashed line. And that's just no good. And you're going to say, well, what does this have to do with demand-controlled ventilation? Well, it has a lot to do with demand-controlled ventilation because a lot of times we're using damper limits on our DCV, which I'm going to explain to you later in this presentation. But this is really an argument. This argument is whether you're doing DCV or not doing DCV, when we don't control outside airflow rates into a building, we are out of control. Okay, and it's that simple. The building's out of control. You can't get good temperature control. You can't get good humidity control. You're wasting energy, or you end up with an indoor air quality problem. Okay? I mean, that's why, 40 years later, I'm still doing this. Okay? Damper issues. We have damper-induced issues. Okay? What are we talking about there? Well, there's three basic things that dampers have problems with. Hysteresis. Hysteresis is, hey, bring the drive shaft back to the same position. There's enough slop in the linkage. All the blades don't go back to the same position. So if you were relying on that position, you're going to end up with different flows. Binding's pretty straightforward. Damper blades bind all the time. Basically, the bearing systems in dampers are pretty poor for the most part. There are some great ones out there, but you will get binding on a lot of different dampers, as well as deterioration of seals. Okay, and all those things are basically changing the opening of the damper. I don't care if you're doing actuator feedback or not. I don't care if it was set up perfectly by test and balance or not. It's not going to come back to the same flow every time. Okay? And again, here's some data. This is from our facility, and we're using a very good damper, in my opinion. We're using a Tamco damper. I've seen this on other dampers, no problem. We're just basically, when you look at the data set on the left, okay, we basically set 100% of set point. And in this case, we set 100% of set point coming from fully open. Okay, I could have done this the other way around. It was shifted the other direction. It doesn't really matter. Okay, but so we come from 100% economizer to 15% damper position. We get the red data set. We come from night setback or damper being closed to 15% open. We get the blue data set. The two data sets are 20% apart. You can't rely on fixed damper position. You start to add that to wind effect, stack effect, fan speed variations, binding problems. You have no idea where you're at, okay? And so you have to measure it. Once you measure it, you can kind of control it out. Or if you can't control it out, you go into airflow alarm because you're like, oh, I can't control for all this mess. And so, I'm going to be in an active airflow alarm. Okay, so you look at all these different factors. To me, it's like, okay, obviously we need to do something here. Okay? Now, the logical conclusion for most people should be, I need to control ventilation for acceptable indoor air quality, but also to save energy and also for good temperature control and humidity control. Okay? Stop blowing money. Stop telling me the stuff costs too much money. Okay? And start getting these buildings working right. Okay? You look at the cost to properly measure and control outdoor airflow rates and compare per square foot of floor area, for instance, and you compare it to what a building costs per square foot of floor area. And to me, it's a no-brainer. Okay? Okay, now we're going to talk about demand control ventilation, the real thing that we actually have come to this presentation for, but it's important for you to recognize that how we started is very important. We're doing this all to improve indoor air quality, and all of this is going to end up working out that it's based on, bringing in the proper amount of outdoor air to dilute the contaminants, okay? So the first thing we need to do, and this audience, we have people from all over the country. So we have folks that are dealing with 90.1 and folks that are dealing with California Title 24, so we're going to talk about both. Up until recently, 90.1 and Title 24's requirements for DCV were almost identical. But during COVID, 90.1 kind of expanded the scope of DCV, which I thought was kind of ironic because, during COVID, both ASHRAE and the CDC were saying, hey, we need to disable demand control ventilation. So it's like, well, why are we going to expand the scope? And it's a lot harder now to just say, well, this is when you do DCV and when you don't. So on the left there, 90.1, I didn't put the table, and I don't really want to get into this, but it basically says demand control ventilation is required for spaces larger than the floor area shown in table 6438 based on an occupant outdoor airflow component and CFM per 1,000 square feet. It's just a little more complicated, it's a little more expanded, so more space is required. Again, it has a lot to do with what I said earlier. I'm sorry if I'm offending anybody, but is it about energy or occupant well-being? Okay. So when we go, to the right there, California Title 24, Part 6 is pretty much what 90.1 used to say, which was demand ventilation controls, complying with their section are required for space with a design occupant density greater than or equal to 25 people per 1,000 square feet. Okay, so, they're similar, but they're no longer identical. Okay, so that's when it's required, and that's either defined by 90.1 or Title 24. When it comes down to what is the definition of DCV, except for Title 24 Part 6, it's based on Standard 62.1, okay? And basically, what I have there on the left is, I'm just going to read what I have my highlights in red, okay? Breathing zone outdoor airflow shall be reset in response to current population. Nothing to do with actually CO2 in terms of by definition, which is going to really set me up for this presentation because when we talk about CO2, yeah, there's a relationship between CO2 and occupancy, but it's not a population counter, okay? And then there's another section there below it, and I think this is important because I see a lot of folks do DCV that don't pay attention to this. Breathing zone outdoor airflow shall not be less than the building component, the floor component part of Title 24, or of Standard 62, and or that required for building exfiltration during high moisture periods. Okay, so that's basically what Standard 62 says, and I want to make sure everybody's understanding that. It's like, hey, by definition, you're bringing in outdoor air based on the current population. And honestly, the logic there on the right is doing just that. If you wanted to truly comply with Standard 62 the way it's written, and the way it makes sense actually, is you would calculate you would measure the population in the zone, you'd calculate the required outdoor air, you would compare it to your limits, really, if you had a perfect count, you would never have to compare it to your limits on the high end. But on the low end, you might say, well, I have local exhaust, toilet exhaust, other exhaust that I have to deal with, or I have a certain amount of need for pressurization. So you'd set your limits, and then that set point would go into your control loop, and that would be how you control your outdoor air. And that would be single zone. For multi-zone, I'm going to talk a little bit about multi-zone a little bit later. And that would also be applicable. It would work pretty well on multi-zone recirculating systems, and of course it would work on DOAS systems. Okay, so that when you look at how deep do you want to get in the Standard 62? Well, Standard 62 basically you calculate the breathing zone outdoor air based on tabled values for rate per person. Based on the type of space it is, right? Times the expected population, and then you have the floor area component times the area, and that's fine. That's how you would normally use Standard 62 on non-DCV spaces. But when you're doing DCV, 62 really kind of turns into an operational standard, and you kind of have to replace the expected population with the current population, because that's exactly what it says. Okay, and so anything that you're going to do DCV, if you're going to use a method that doesn't count the people, then we want to see that is the method you're using actually comply with this. So we're going to do a little bit of that, especially when we get into CO2. California Title 24, their definition's different. demand ventilation control shall be maintain CO2 concentrations less than or equal to 600 parts per million plus the outdoor, which is typically 400. So typically in California, you're dealing with 1,000 parts per million, at least currently, okay? And so the question there is, does that mean just control the outdoor air CO2? Well, I'm going to show you why that's not the best idea, okay? But right now, I'm just going to kind of defer that conversation a little bit, okay? So we're going to go into CO2. All right, so, you know, my buddy Daryl at EBTRON knows that I've about had it with CO2, and you know, I've been working on explaining to people some of the problems with CO2 and for ventilation control since about 1993, and I published a little bit on it. And you know, I had one paper in particular rejected because they didn't like my position, even though it was technically accurate. And I'm just kind of fed up at this point in my life, okay? So, but I am going to go through this because I have a lot of experience with it, okay? So, you know, let's just go back historically, again, to, I could go before, not 6289. CO2 was in the standard as a high limit at about 2,500 parts per million prior to 1989. But in 1989, language got into the standard that I think really changed everything, okay? And so there was a sentence that said, comfort criteria are likely to be satisfied if the ventilation rate is set so that 1,000 parts per million CO2 is not exceeded. It really didn't mean it met the ventilation requirements of standard. It just kind of, it meant exactly what it said. It's like, you know, body odor should be controlled if you're 1,000 parts per million or under. But people read that as, oh, ASHRAE says that's what we're supposed to do. And in 1999, the language only got changed a little bit because really probably the 1,000 part per million, if you did the calculations, wasn't really right. It was closer to 1,100 parts per million, and in a lot of areas the CO2 level varied, so they just made a change to say, hey, a 700 part per million rise. You know, it was basically the same thing. Okay, after 2001 and 2004, it actually, any references to CO2 were removed, and now here we are in 2022, and it's really back in your face again, as we'll see. But at any rate, it was removed for a long period of time. And the question, what's happened over the years, and what I've seen over the years, is people have been so misled, and it's really unfortunate. Okay, people have been misled to think that CO2 is a contaminant. And people have been misled to think that a low CO2 level means you have adequate ventilation. And we're gonna talk about both of those today, okay? And like I said, if you know me, you can tell I'm pretty much wore out on this. I'm not going away, but I'm wore out on it, okay? Let's just start with prior to the current version of Standard 62. You know, in the IAQ procedure, carbon dioxide was listed as a contaminant, and you might need to get your magnifying glass out to see this, if you're depending on how you're looking at this. But you know, basically, OSHA considered CO2 to be a harmful contaminant at or above 5,000 parts per million, and most buildings will not get to 5,000 parts per million, although it's possible if you're running the IAQ procedure and you reduce the outdoor air to really low levels that you could get there. But the bottom line is, that's an 8-hour exposure, 5,000 parts per million. We're typically not getting there. It's not a contaminant of concern for the most part. There are some papers out there that talk about CO2 and cognitive processing, but there's also a relationship, as you're going to find, between CO2 and ventilation. And so it's going to be not real straightforward, okay, on the CO2 deal, if it's a contaminant or not. It's certainly not a measure of indoor air quality, as so many people think it is, okay? And then you think about during COVID, you know, I mean, parents were giving kids CO2 sensors to bring to school. First of all, the CO2 sensors were probably garbage that they were bringing anyhow, weren't very accurate. And second of all, they thought, well, if the CO2 level was low, it's great. Well, I can show you when those kids walked into the classroom, the CO2 level was low, and that was probably the most dangerous part of the day. So, so much for that. Well, if it's not a contaminant, it's like, what are we doing? And why are we doing this? And, it's really not that hard to see why we're doing it. However, one of the flaws that we have continued to use in this analysis for as long as I've been around, and I'm 62, and I started, in the business when I was 21, okay? And we've assumed, because the math is easier, and mechanical engineers are not really chemical engineers, we've just assumed steady state. Because when we assume steady state, we don't have to look at the volume of the space, and we don't have to look at the rate of change of the CO2 level in space. We just say, we're at steady state. Well, anybody who understands this at all would say, if you're doing DCV, you're rarely at steady state. You're saying the population is changing, and you're resetting the outside air. But we're just going to ignore that, okay? So, and I'm just going to go along with this and say, let's ignore it, and let's look at this steady state model and assume it. And now, can we make a relationship? What is this CO2 thing all about? Okay, so on the left there, you've got outdoor air coming into some ventilation zone. And because we're at steady state, we're going to have to say it's a constant flow of outdoor air, okay? And outdoor air contains CO2, all right? It contains low levels of CO2, typically 400 parts per million, plus or minus quite a bit, actually, depending on where you are. And then within the ventilation zone, we have occupants. And each one of us produce CO2 as a byproduct of respiration. Okay? So the more of us there are, the more CO2 there is. Okay? And actually, there's different things that even affect how much CO2 we produce. But right now, we're going to assume, we all produce the same CO2, the amount of CO2. Okay? And so the outside air that comes into the space doesn't get, it gets force exfiltrated or exhausted or relieved mechanically, but it's going to leave. And it leaves at the new elevated CO2 level of the space, okay? Well, that's all you need to make a steady state equation. A steady state equation is the goes intos equal the goes out ofs, okay? So one of the goes intos is, what we have there as COVOZ. Well, what is that? Well, CO is the concentration of CO2. You could either put it down as parts per million, or I did it as cubic feet of CO2 per cubic feet of air, just to keep it dimensionally straight, and because my background was in chemical engineering, so it was, it's just how we do it, okay? So COVOZ. So that's the outside airflow rate, and times the concentration of the CO2. That's a goes into. Another goes into is G times P. G is the CO2 production rate of the individuals, and P is the number of people. It's dimensionally the same as the first term, so it's still an equation, okay? More people we have, the more CO2 we're producing. Those are the two goes intos. What's the goes out of? The goes out of is the air that's either exfiltrated or mechanically relieved or exhausted. And it's the same amount of outdoor air, VOZ, but it's going out at a new elevated indoor CO2 level. So you got an equation. That's a steady state equation. And algebraically, we can rearrange that equation to be the same equation, but maybe be a little more interesting. And when we rearrange it, we can rearrange it for VOZ over P, which, at least in the States here, is outside air CFM per person. So if we know the CO2 production rate of the occupant, we know the indoor CO2 level in the breathing zone, and we know the outdoor CO2 level of the air coming in, and we're at steady state, we can estimate outdoor air CFM per person. That's not a crazy idea, because think back now, ventilation standard 62 was 20 CFM per person for an office, and 15 CFM per person for a classroom. And it ends up, when you looked at 15 CFM per person, average sedentary adult using the data at the time, sedentary being seated, not too active, you'd end up with 15 CFM per person being about a 700 part per million rise. And, people would set, classrooms to 700 plus 400, 1100 parts per million. That's where that came from. It has nothing to do with it being a contaminant. They'd set offices. At 20 CFM, you do the calculation, you get closer to a 550 part per million rise, so you set offices around 950. California being 15 CFM per person would have been 1100, but they're like, the CO2 sensors have errors, so let's just make it 1000. Okay? That's where these numbers came from. Okay? And so it has nothing to do with it being a contaminant. And some of you could sit there and say right now, well, that seems good. And yeah, it's good, but you've got to remember you've made a bunch of assumptions here. Okay? You typically have made an assumption of the outdoor CO2 level. You've typically made an assumption of the CO2 production rate of the occupant. You've made an assumption that the CO2 measurement on the wall or wherever you have it is actually the breathing zone CO2 level. You've made an assumption that you're at steady state. That's an awful lot of assumptions. Okay? So, we're going to have to take a look at that. All right? So, again, this is my, hey, here's your assumptions. Activity level, sex, male, females are different, diet, a little bit of difference between high carb, low carb, or high carb, high fat. Ages have a significant effect on the CO2 production rate, body mass. Somehow I forgot activity level, which is like the biggest. Okay, and then the fact that you're probably not at steady state. So we should look at some of this, right? I mean, you're going to do if you put a flow meter in the outside, or people, I'm going to put a flow meter in the outside. How accurate is it? I want to use counters to set this. Oh, how accurate is your counter? Well, how do these factors affect the amount of outdoor air you're bringing in? Because that's what you're using it for. You're not using it because it's an air quality meter. You're using it as a proxy for how much outdoor air is coming in. So I think I would want to know how much that affects things. So what happens here now, and this is a problem we've had for years, that ASHRAE is trying to address in its recently approved Addendum AB, which was so much better in its original version. It took them 3 versions to get it approved, and I can't understand why, because the first version I thought was perfect. It was just a little complicated, but you know what? If that's what it took, that's what it took. All right. But at any rate, the problem that we've had is that we're setting so many spaces up for this 1,000 parts per million and not realizing that CO2 and ventilation are codependent, meaning you can't speak about one without speaking about the other. So if I took adult males at steady state, 1.3 METs. METs is basically an activity, measure of activity. 1.3 is somewhere around seated, maybe a slightly more active than seated. We got 1,000 parts per million. That's 17 CFM per person. Okay, and that's what that means. It means if all the assumptions were right, you'd be driving 17 CFM per person in space. Well, one of the fundamental problems to date has been Standard 62 in 2004 changed its ventilation requirements. Okay, so that I'm just going to look at occupant default densities from the standard. Your space may be a little bit different, but if you look at a classroom at the occupant default density, it's 13 CFM per person. A lecture hall is 8 CFM per person. A conference meeting, worship space is 6 CFM per person. And like I said, your numbers could be different. But the bottom line, it's not 17 CFM per person. So here you are, you're designing, and this is bigger. This is actually a bigger problem outside of California than it is in California, because they're using 15 CFM per person, okay? But, you're designing a system for either that 13, that 8, or that 6, but you're putting in a control logic to drive the outside air to 17. Now, if you're in a dry climate, that's not really that big of a deal. I mean, you're spending extra money. Your system probably can handle it a little bit, but when you're east of the Rockies and you are in a moist climate and you've sized your system for 13, 8, or 6 CFM per person, and then you're putting in control logic to make it drive to 17 CFM per person at peak load, you have a problem. And I've seen it and seen it and seen it. Okay, and they're trying to address it in this addendum AB. It's going to take a long time to get into code. People need to understand, and I don't think they've done a great job of it, but people need to understand this. Okay, the other thing is those of you that are using the IQP, and DCV is under the VRP, not the IQP. Okay, and it's not under the IQP for a good reason. If you're trying to do CO2 DCV at 1,000 parts per million, and you've made an argument that you're going to reduce the outside air required because of some air cleaning you used, you're still going to be driving 17 CFM per person into that space. Okay? That's not good. All right? And not enough people understand this. And more people do need to understand it. That's why I decided to do this presentation, as a virtual. And then the other problem you have is activity level. Now, a lot of spaces you're applying this on, the activity levels are relatively low, and maybe there's not a lot of variability. But I've seen folks apply this on, workout spaces, for athletes, okay? And so when you look at this, it's like, 1,000 parts per million is 17 CFM per person for a seated adult. But if you have a vigorous workout, it's 103 CFM per person. You didn't design for that, okay? And then, of course, we have age, And I don't even have body mass. I don't think I used any slides for body mass. But then on that previous slide, you do body mass, and it's even higher. Okay, and then we have effective age. 1,000 parts per million for a 9-year-old at 1.3 met is 9 CFM per person. For an adult, it's 17. You're running a lot of these classrooms at 9. I've heard people make arguments. Oh, the kids are more active. The last time I looked at a kindergarten or first grade, well, maybe not kindergarten, first graders, they were sitting there snoozing, okay? So I don't think they were more active, all right? So, what's happening is folks are trying to fit this model into their solution, okay? And there's a lot of problems with this model, okay? And it's not enough people understand that. All right, and I'm hoping some of you grab it and do something with it, okay? The next thing is, forget all that. That was if all your measurements were perfect. And you're just listening to say, David, what? I didn't listen to this to have you tell me that nothing I'm doing is working. I plan to have an answer, an improvement, okay? But you have to understand the problem before we can talk about the answer. Otherwise, you say, I don't need to do anything different. Okay, so when we look at, now that we know that the measurement is really related to how much outdoor air we bring in, okay, now you have to look at what does measurement uncertainty mean. So I have a CO2 sensor on the wall, and it's giving me a CO2 level. Is it right or is it wrong? And people can make arguments, well, CO2 sensor might be 35 parts per million off, or it might be 100 parts per million off. But the one thing that I don't hear very many people talk about is, does it matter where it is? And so in our building, we put 12 CO2 sensors in what we call our brain gas room, which is a 5,000 square foot room. They're all at 6 foot high, and they're all calibrated and read the same when they're together. And they read up to 200 parts per million differently, depending on where they're located in the space. So which is the right one? I hear people say, I use a sampling device, so we put everything through one sensor. It's not just the sensor. Is the sensor represent the CO2 level, the average CO2 level of the breathing zone? Okay, so when we take a look at this, okay, I'm saying, hey, 100 part per million uncertainty on the measurement in the room and the 50 part per million uncertainty outdoors. And what does that do? Well, let's look at this slide a little more. Let's get you to focus on the graph, okay? So if we're dealing with standard 62 right now, and we're dealing with a classroom, 1,000 square foot classroom, 35 students in it, design. The black line is the standard 62 required ventilation between 0 and 35 students, okay? Now you know the relationship between CO2 and ventilation. If it was perfect, it's CFM per person. So it's the red line. So it's going to have a crossover point. It's going to overventilate at higher populations and underventilate at lower populations, and it's going to go to 0. Okay? Well, when you take a look at now adding the uncertainties on this, and for whatever it's worth, I have a variation of this that was published in 2004, so it's not like, oh, this is new stuff. Okay, it's not new stuff. All right. The ventilation uncertainty gives you that red scatter, and that means that if you were just doing pure CO2 ventilation control without any limits, okay, at the high population you could be overventilating by 70%. That is certainly not what you intended to do. And again, it's a bigger problem when you have high moisture. I've seen in Florida where they don't have economizers. This create not just temperature and humidity control problems, but they've sized their intakes in a lot of cases for max water carryover at design CFM. And now they have a water carryover problem. I've seen EBTRON flow meters look like chia pets in Florida. Okay? So you have this uncertainty. It's a problem. What are you going to do about it? Well, you got wasted energy, thermal comfort issues, pressurization problems, on the high end, and depending on what you did on the low end, you have, under ventilation, pressurization problems, IAQ problems. So, this is why we had to start this presentation with just basically fixed set point control problems, because a lot of people say, well, I'm going to set limits, and I'm going to set limits with dampers. And so, now after our discussion in the beginning of this, you should realize that that doesn't work. Okay, so how much uncertainty is there? Okay, well, we said, hey, at a constant fan speed, the uncertainty could be 50% just from wind and stack and damper issues. Okay, and then on top of that, if we have a system that has turn down, fan speed turn down, okay, now that's going to track with the turn down. So you end up with this. Is that acceptable? I mean, you really don't know where you're at. No, that's not acceptable. And so the way that you deal with this is you don't use damper limits. You integrate outdoor airflow measurement. Either if it's a recirculating unit, you implement it at the air handler, and if it's a DOAS unit, you implement it at the ventilation zone. Okay, and then your limits are maintained within the uncertainty of the flow measurement that you're using. And that's a significant improvement. Okay, and I do the same thing. That was for ASHRAE 62, or most of people. Title 24 does have similar problems. You have a lower limit that you have to deal with. Because you're at 15 CFM per person, you're a little bit tighter, but it's still not great when you add the uncertainty to it. Okay, and all the same problems. Setting the limits doesn't really, with dampers isn't going to work. I guess I saved myself a slide there by not doing the same thing. No, you improve it again by setting these airflow limits with the airflow measurement device. And really you have two control logic options, okay? The one on the left is deadband control. It's pretty common for what you're doing probably today, where you're basically, instead of going from a min position to a min-max position on either damper or speed, okay, what you do is you control the min to the flow and the min-max to flow, and it's deadband control. So, I don't know, let's see, the best way to describe it is, hey, I'm under 400 parts per million, or 400 parts per million, I go into, people go into the space, I run at the min, we get to 1,000 parts per million. If that was a set point, we go to the min-max. We have 100 part per million deadband, so when we go below the deadband, we go back to the min, and you throttle between the two. Okay, that's one way to do it. But when you're doing with the flow measurement, it's much better because you really are setting these limits. And then on the other side of it, on the right, modulating control, which I have a tendency to prefer it, it's going to vary the outside air to maintain 1,000 parts per million by modulating the flow. Both of them essentially will keep your space at whatever your set point was, but one is going from two extremes of outdoor air to another, one extreme to another. The other one is kind of modulating through. It just depends on what you want. The control logic on the right, for those of you that are controls people, it's the same control logic you use on a VAV box for temperature control. Instead of having a VAV box, the room temperature goes into a control loop or a reset loop that compares the set point to the temperature, and it outputs an airflow, and it basically sets it between a min, if it's below the min, it sets it to the min. If it's above the max, it sets it to the max. And anywhere in between, it's in between. You just are replacing the temperature with CO2, and it's the same basic strategy. And it doesn't have to just, the output of that control doesn't have to be very simple, just modulated damper. It could be a very complex sequence, okay, if that's what you need. So that's the control logic, all right? And the good news is what happens when you do that, when you set the boundary on the top, you actually will go into CO2 alarm, because the CO2 sensor is calling for more outside air, so you're not going to be at your set point, okay? The good news is Standard 62 and its addendum AB did add this language here on the left that said ventilation rates are not required to be larger than the design ventilation at design occupancy regardless of CO2 concentration. So you've got an airflow meter in there, you're doing this, you're going to say, hey, I'm at design, okay? And Title 24 is pretty much identical. Outdoor air ventilation rate is not required to be larger than the design outdoor air ventilation rate regardless of CO2 concentration. So those are good things, okay? We have another method, though, that I originally put out, how to be close to 2010, that we talked about, hey, if you bought into the steady state relationship and you measured the outdoor airflow rate coming into the unit, or the outdoor airflow flow rate into individual ventilation zones, you had one more piece of the steady state equation. You had the VOZ, and once you had the VOZ, you could estimate the population. And so when you estimated the population, now you could do this more closely, follow the Standard 62 required ventilation. For those of you in California, this doesn't really do much for you, but for the rest of us, it does. And as long as you anytime you're doing this, you bought in the steady state. And so I'm showing the same measurement uncertainty. It's definitely a significant improvement. It doesn't require any more equipment. It actually is a lot better on the lag, which we haven't talked about yet, okay? And this is basically the control logic for it. It's more like it just follows, you calculate, you're estimating population using CO2 and measured outdoor airflow. All right, now we are going to talk about lag, and before I can talk about lag, I need to take a minute, and so I'll be back in I need a little break. All right, that's not too bad. Had a glass of wine. I guess Jessica left me this glass of wine. I don't know where the heck she is. My jacket. So I'm good. So, okay. I think, like I said, we're going to have a few breaks during this. Hope you're all hanging in there. So, the way I think I'm going to do this is when I get done, I'll still put some more time on so you folks could have a little bit of a break, and I'll throw up what I call the Morgan clock, okay? And for those of you who don't know who Morgan is, which you probably don't, Morgan's our Chihuahua that passed away a few years ago, but for some reason I can't get over it, so I keep using the Morgan clock and stuff. So, you know, we'll see what kind of time we can put on this, give you a little bit of a break. And I should be, the way this is set up today, I think I should be able to get another break, maybe 2 breaks in. So, you know, you don't want to sit here and listen to me. So, so I'm gonna actually go back in, set a little clock for you, and go on, do some more, and then we'll come back and we'll do a break. Maybe I can find my wife. I have a feeling I know where she is, which may or may not be a good thing. I don't know, but we'll see how it all goes. So so I'll see you on the next break. Happy holidays. Okay, we're halfway through our break. 5 minutes left, so probably time to think about starting to finish up whatever it is that you were doing.
Okay, we're down to 2 minutes left, so we're going to get this thing started again in 2 minutes. If you do have any questions once this is done, you can either give me a call or send me an email, and I'll get back to you. Thanks. Okay, break is over. It's time to settle back down and so we can get this thing started again.
Okay, now we're going to talk about lag, okay? So one of the big problems with CO2 is this assumption of steady state, and the reason for that is pretty simple. I don't know if you really think about it, but you know, when you walk into a space, the CO2 level in a space is, let's just say you came in after a nighttime setback operation, or you even did a pre-purge or whatever you did. The CO2 level in the space is going to be pretty much what the CO2 level is outdoors, okay? And then you bring people into a space and they're breathing and producing CO2 as a byproduct of respiration, but that CO2 level doesn't immediately go up, okay? It just gradually grows because you have the volume of the space, all right? So that's a big problem. And, you know, the way to kind of illustrate it, I guess, is, you know, here's a space, beginning of occupancy, not a lot of CO2 in the space, people come in, it takes some time for the CO2 level to go up, people leave, it takes some time for the CO2 level to go down, and that creates somewhat of a problem, okay? Because remember, everything we've talked about so far, everything has been based on the assumption of steady state. And when you're doing demand controlled ventilation, you're not at steady state. So one of the things is that, you know, ASHRAE 62 has a requirement that current population estimates or indicators used in DCV control calculations shall not result in ventilation rates that are less than those required by the actual population when averaged over the time period determined by section 6252, or 1 hour, whichever is less. And typically it ends up being 1 hour. Okay, and so we're going to look at that and see if these methods actually meet that requirement when you're doing CO2 DCV, okay? So, one of the things, and I think this is good, but I'm not in love with the way that it was done, okay? It's an attempt to make things better. One of the problems with the traditional CO2 DCV that we've kind of already talked about, like 1,000 part per million CO2 DCV, is the way that these strategies work is they really don't bring in the design or high enough outdoor airflow rates until you get near the 1,000 parts per million, or the set point, whatever the set point was. So the lag is a real problem. The other problem is the 1,000 parts per million we've been using isn't really the right number. I mean, you saw that in what I already showed you, that it's very dependent on the type of space, and it's very dependent on the occupant, you know, what their activity level is, etc. You know, so you know, ASHRAE, I don't know why they had to do this in the standard. It used to be discussed in an appendix, and I think that's where it belongs. Standard 62 has rarely told people what to do and how to do it. But for some reason, when it comes down to demand control ventilation, they've taken on the how to do it. The definition hasn't changed. The definition is, you know, even with this addition that I'm going to talk about from this addendum AB, okay, you know, the definition of DCV is still provide the ventilation for the population. Okay, why put this in? I'm not sure, as in the body of the standard. But anyhow, what they're doing is they're actually providing a method for doing CO2 DCV in the standard, and it is an improvement over what we did, although I'm not sure that everybody will do what they need to do. So I want to just go through this with you. And I'm only again going to read my red notes. You can read the whole thing if you want. But upon a rise in measured CO2 levels above C ambient is your starting point, ventilation shall be increased proportional to the difference between the zone CO2 concentration and C ambient. So really what we're doing here, what they're saying is we're going to do a linear increase in the outdoor airflow rate as the CO2 level increases. And what that will do is it will improve the problem we have with lag. It's still a steady state issue. There's still problems I'm going to show you. They've set some CO2 levels in table 6.1. I do have some problems with those. The original addendum AB and even the second version of AB showed you how to make these calculations, and I don't think they were all that difficult to make, okay? And now we've put in table values, and then look at what it says in the informative note. On the table values, it says the CO2 values in table 6.1 are only for the purpose of implementing CO2 DCV. They are not intended to be and should not be used as indicators of indoor air quality. Why are they there? Okay, and I'm sorry, something happened to my throat in the last 10 or 15 minutes. Anyhow, what it ends up doing, a simple way to look at it is, you know, and it's really pretty specific right now on a single zone. On the single zone or a DOS ventilation zone, I mean, basically what you're going to do, you know, is you're going to reset the outside airflow rate based on the CO2 level between, you know, ambient outdoor and whatever the design CO2 level is, or most likely you're going to take the table value. You know, so, but they don't tell you how you're going to do that, all right? So I think what's going to end up happening is some folks are going to say, well, I'm just going to reset dampers, or I'm just going to reset fans, or whatever, and it's like, well, that isn't necessarily going to work, okay? If you reset the airflow set point, yes, I think this is going to work. And so I have the control logic there on the right. It's pretty straightforward. You know, you're basically just doing a linear reset between the min and the max. But keep in mind, because of some assumptions you've made, they make a statement that, you know, when you're at design, the CO2 level should be at the, you know, the CO2 level and the design outside air should be, you know, the same. It's not going to happen. You've made assumptions. They'll never line up right. Okay. So here's the deal. So if you look at it, basically, if you look at that graph on the left, what you'll find is what I have the corresponding CO2 level, you know, basically is the axis on the right, and the amount of outdoor air you'll provide is the axis on the left for this classroom example that I've been doing. And what you'll find is that, and I don't think that this is a bad thing, that this method, the black, which is the ventilation, the black line is the ventilation required by standard 62 for that population, and the at steady state, okay, what you would provide is the dashed curve, which is in excess. So to me, anytime you're providing excess outdoor air in a DCV strategy, it's better. But I have a bunch of comments there on the right, and I think I'll just go through and read them to you. You know, so, you know, you're going to reset the airflow set point to measure the airflow rate. That's the way I think you should do it. I don't think you should rely on damper position. I think that's a bad idea. We've already talked about why. Because you can't compensate for fan speed, wind, stack, pressure, or damper issues if you do that, all right? You know, the outdoor airflow rate provided will exceed the minimum ventilation requirements of ASHRAE 62, but I think that's okay at mid-populations. And then I say, be aware that the design ventilation rate will not result in table 6.1 value for CO2 max. It's just very rarely going to happen that way. It will typically result in higher CO2 levels at the design maximum ventilation rate, which is fine. That doesn't have to, though. It could be either side. My problem here is, because now what you have to understand is the CO2 level in the space is variable. There's no way to really know that it's the right CO2 level, right? You're going to go into a space, and unless you counted the people in the space and measure the amount of outdoor airflow that's coming into the space, or the outdoor airflow rates going into space, you have no way to know if it's right. And I'm not so sure that wasn't by design. There's no way to verify this. And verify that it's actually performing properly. There is no way to do it unless you're counting the people and measuring the airflow rate. And that's not what people are going to normally do. So you've got this CO2 level that could be anywhere from, you know, ambient outdoors to whatever the table 6.1 or the calculated value is. So you just don't know that it's right. I think the other problem when I talk to air balancers and commissioning agents is how do you know this is actually working during operation? You're not in there when the facility's occupied. Okay, you're going to look at min and maxes and you say, yeah, I got my min and my max. That doesn't mean anything. Are you providing the proper amount of ventilation, outdoor air, during operation? And there's no way anybody's going to know. And that's really what's sad about this whole thing. So that's something I want you to think about, okay? It's not, you know, I'm not here to change the universe, but I am here to point out some problems, okay? Now, earlier I talked about the alternate method that we came up with a long time ago. It still assumes steady state. But because it estimates the population, you don't have that overventilation in the middle of the, you know, midpoints. You're actually more tracking the requirements of standard 62. To me, you just have to decide which one of these methods you want to use. I mean, everything I've shown you so far uses the same equipment. It's going to use a CO2 sensor and an airflow meter. Okay, and it just comes down to how are you using it. The one nice thing about the language in the approved AB is, you know, it talks about the method that they want you to use, but it says exceptions. Other DCV control logic shall be permitted to be used when it can be demonstrated to comply with the section. So this would also comply with the section. So you just have to decide what you want to do. Okay, and to me, it gets rid of the overventilation in the midpoint, but I'm going to show you some other things about it that, you know, maybe it's not what you want to do, okay? So, the reality is, we're not at steady state, Okay, and so for me, for the last, I don't know, 10 or 15 years, I've been calculating out and saying, well, we're not at steady state. That's the imaginary world some people are in. We're in a very dynamic state when we're doing CO2 DCV. And so, I created it's not a difficult model. It's just kind of bins things out into minutes. And it's basically an ins equal the outs. And it looks at and I'm not expecting anybody to look at this and see exactly what I'm doing. But it's just a simple spreadsheet, really. And it looks at the ins and the outs. It even can take into account CO2 removal devices if you wanted to, okay? And it looks at what for various control strategies that you're using, based on the CO2 level in the space, how much outdoor air are you bringing in? Okay, so I think that's really important because that's what's really happening, okay? And so what I decided to do is I said, let's look at, just for today, this model is so good that I can bias the measurements, I can bias the CO2 production rates of the individuals, I can do all kinds of things with it. I can look at error of different measurements. To make it simple, just for discussion, I'm saying that there are no errors, okay? That we know exactly what the CO2 production rate of the occupant is, and we know exactly what the CO2 level of the space is. And so here I'm looking at an office space, because one of the things in this table 6.1 now is it actually gives a CO2 set point for the office space, and I think that's almost a crime, because an office space is a low occupant density space. That means it's going to take quite some time for the CO2 level to get high. And some of you, like myself, have probably seen some pretty high level TV shows that talk about, how great it is because the CO2 level in an office space is so low. And that means that they're bringing in lots of outdoor air. Well, that's not what it means. Okay, so what are we looking at here? How do I describe this to you in a webinar? And, well, basically what we have is I'm looking at actual requirements of standard 62 in real time, which is the solid green, which you don't see because there's a dash black on top of it. And then I'm looking at the time average, and I'm actually looking at the most favorable case for the time average, because the time average isn't, say, backwards or forwards, it just said over any 1 hour period. So I'm taking the best case here. And so I'm marching basically 5 people per 1,000 square feet into an office space. I am not moving people around in any of these examples. If I start moving people around, it gets even worse, but it gets a lot harder to look at, okay? So I put 5 people into this office space. The amount of outdoor air required is the green, right around 85 CFM, okay, total for the 5 people. Using your traditional 1,000 part per million CO2 set point, all right, control logic, all right, what you'll bring in is the red, okay, and the red is significantly less than what you're supposed to bring in. And the blue, so the red and the green go with the left vertical axis. The blue is the actual measured CO2 level, which goes with the right vertical axis, okay? And so what you find is, over time there, for the first, 3.5 hours or so, the CO2 level is low. And to people that don't understand this, they're like, oh, my air quality is so good. Well, it's not so good. You're providing significantly less than the outdoor air required by standard 62. And in fact, it's not until you got to 3.5 hours that you met the time averaging requirement. Okay? All right, so I don't want to be in that office. Maybe you don't care, but I care. I don't want to be in that office. And, and that's assuming it was set up right and it's working right and there's no errors. So now I look at all the other methods and I say, well, how would the CO2 airflow population estimation method that we kind of, put out there 10 or 15 years, probably 15 years ago, like I said, and it takes a while. In fact, it never gets technically to where we've gotten to the time averaging requirement. So it's actually off to the right of this graph. After 4 hours, we still haven't hit the amount of outdoor air we need. Now, you can make an argument that, hey, if you're within 5% or 10%, you're close enough. And I would accept that, actually, okay? And so then we take a look at the ASHRAE 62 Addendum AB. If everything worked perfectly, I mean, you're actually resetting the airflow set point. And it's the same thing. It really doesn't get to the point where you have gotten to the requirement for the time averaging on the outdoor air you provided. Now again, you do get to within 5%, but you're still talking hours. Okay? You don't want to be in a space that takes hours to get to the minimum ventilation requirements. Okay? That doesn't make sense to me. All right? Yet, when you look at the AB modification to standard 62, it actually gives a CO2 set point. That 600 parts per million is the differential. So it's basically 1,000 parts per million, exactly what I've been doing. And yet it's in there, but it'll never meet the ventilation requirements of that same line. It will maybe by the end of the day. So why is it in there? It should be not applicable, okay? And then I can look at these other set points. I mean, I'm not going to kind of go off on those. The reality is, like we talked earlier, the CO2 levels actually, if you calculate what the set point should be, are actually higher. So that reception area that's right below the office space at 2,100 parts per million says you should be setting a reception area to 2,500 parts per million. When you all the changes that were done by this AB, yeah, they convinced some people that the changes were made to improve the lag problem, but the reality of it is this is reducing the amount of outdoor air once again that's coming into our spaces. I've been doing this since 1984. So I came, from the problems of the 70s. We're doing everything that we did in the 70s and 80s all over again because of energy, okay? And we're really losing track of why we provide ventilation. And you don't have to agree with me on that. It's pretty clear, okay? So anyhow, I'm going to go to some classroom examples, all right? So now I'm going to look at these 3 different methods in classroom. So here I have a classroom, and again, if I was moving the population around, it would be much different several hours into this, but also a lot more complicated to look at. So, I'm just bringing in 30 students into this classroom, okay, and that's my design for the classroom, all right, and this is the traditional 1,000 part per million set point. So it's a traditional either deadband control or modulating control. They both end up doing the same thing. And what you find when you do that is, a little under a half hour, you'll get to the ventilation that you needed, okay? You won't get to the 1,000 parts per million, but that's okay. You will have gotten to the ventilation you needed for that design before you got to 1,000 parts per million, but that is okay as long as people understand that, okay? And you know that you're actually at the limit, all right? So the strategies that we talked about earlier would say, yeah, I'm at the design outdoor air for the space. I don't know that this is really terrible. A little under a half hour, maybe you do a pre-purge in the morning, and that kind of deals with this, okay? The CO2 airflow estimation method that we use, it does take a little bit longer. It's about 45 minutes or so, and the proposed method by Standard 62 takes a little bit longer, about a half hour. I don't think any of these are really the end of the world. Okay. Where the problem lies is because it's DCV, the assumption is you got variable population. So here we have this same space that was designed for 30, but it only has 10 people in it. So now when we do our traditional 1,000 part per million set point, we never got to the amount of outdoor air we needed. That'll run all day long like that, and we're under ventilating. So, traditional DCV, what we've been doing for years, if it was even working right, never mind the errors I've already talked about earlier, it never provided the amount of outdoor air needed on off populations in a classroom, okay? But the CO2 levels look great. And it's really sad that people don't understand that. When we look at the CO2 airflow population estimation method, it does improve this, but it's still almost 2.5 hours. And when we look at the addendum AB approved stuff, it's actually considerably better because what happens here is you actually are providing more ventilation, okay? So in some respects this is better, but you have to understand that you only have to provide the green, you're providing the red now, okay? I can't really argue with that from an occupant well-being perspective though, and you still are saving energy because you are reducing the outdoor air. So that works. It does work better. Okay, so you decide what This is a presentation where you don't digest it in one shot. Okay. But if you want to do DCV right, you need to incorporate airflow measurement for limit control as a bare minimum. And if you've gone to limit control, you might as well do one of these more improved methods, whether it be the CO2 airflow population estimation method, or if you really just want to comply with what it says in Standard 62, that's fine. I mean, go with that method. It'll have a tendency to overventilate a little bit, but that's all right. I wouldn't use it on office spaces or low occupant density spaces. I think that's crazy. But you also have to keep in mind that all those examples I just showed you didn't show any of the uncertainty of measurement that we talked about before. CO2 is still a problem to me. Okay, I mean, it really is. I mean, if I told you, if you go back to some of those slides that are showing 60 or 70% overventilation, if I told you you were going to put an EBTRON in the outside air and it was going to read 70% high, you'd laugh at me. But yet you do this every day of the week. Okay? Now, that brings me back then to revisiting population-based DCV, and I really have a problem with the fact that ASHRAE has not really done a lot to support or promote this method, okay? Even though the definition of Standard 62, I'm going back, I showed you this before, this is in the ventilation rate procedure on the left there. For DCV ventilation zones in the occupied mode, breathing zone outdoor airflow shall be reset in response to the current population. Why aren't we looking at that? I mean, it's allowed to use occupancy counting devices, but we're not actually promoting that. We're not saying, hey, this is the best way to do it. And one of the reasons why it's the best way to do it is there's no lag error. I don't understand why there's not a whole lot of push towards doing this. All right? You measure the population, you measure the outdoor air, you control the outdoor air. Easy. Okay? I don't get it. Okay? And the other, the thing about it is, people say, well, what counting error? Well, here what I've done is I have a counter in a classroom that's off. It's off plus or minus 3, all the way down to 0. That means when there's one person in there, it might read 1, or it might read, it might read 0, or it might read 4. It's a lot of error. But when you look at the scatter associated with that, okay, the green scatter, compared to some of the other stuff I was showing you with CO2, it's much better. I mean, even plus or minus 5 count on a 35 person classroom is going to outperform CO2. Why are we not going in that direction? I do not understand it. All right, that's where we should be putting our resources. And then on top of that, when you're doing population counting, all of a sudden multi-zone recirculating systems are easy, okay? Because you can calculate the ventilation efficiency in real time, okay, by knowing the airflow rates to the ventilation zones and knowing, the outside air. You can make decisions on adjusting zone supply flow rates, either increase and add reheat, or use something like parallel or series boxes to pull unused outdoor air. Why aren't we doing this? Why aren't we looking into this? This would make VAV systems very, very efficient, okay? And, there's lots of things we could be doing, and we're not, okay? And I have my theories as to why we're not, but I'll leave my theories to myself. You folks are pretty smart. You can figure it out, all right? So there is a lot to be said about measuring people. So just remember that DCV doesn't mean CO2. CO2 has some issues. There are ways to improve CO2, and ultimately I think we should get to measuring the occupancy of the space, okay? Now, that really gets us into this IRMM operation. Basically COVID really drove a lot of changes that we had to make. And I was very pleased with ASHRAE's initial response to COVID, and their first position document that really came out a month after COVID was really a problem. And, it talked about, I'm not going to read the right there. You could, and basically going to paraphrase it here. It said, hey, we have an infected individual there. And, when they're talking or coughing or whatever they're doing, there's this plume of air that comes off of the individual, and the larger aerosols fall to the floor, the larger particles fall to the floor. That's really what I should be saying. And in that 3 to 7 foot range, and that's what kind of got our 6 foot spacing going. But not all the particles fell to the floor. Some of the particles were desiccated, and it didn't have to be from heat or anything like that. I just show that because people understand, oh yeah, I got some dry air, it's desiccating these particles. Those particles don't fall to the floor, they get suspended. And if you read through what they say there, they're like, hey, these particles could stay infectious for hours, days, or even weeks. And those were really our problem, and are our problem. Okay, the ones that fall to the floor they can be a problem. They get kicked back up, all right. But the bottom line is our HVAC system isn't going to do much with those. But what we have to do is either dilute, basically when we go all the way back to the beginning of this presentation, we have to either dilute, or remove through filtration, or kill these particles, right? So that's what we're gonna, that's what we're using our HVAC system for. One of the things that Standard 241 came out, which they had to. One of the problems was that Standard 62 is really inadequate for when we have infectious aerosols. Okay, so 241 came out and said, hey, we got to increase the outdoor airflow rate during these periods. And it also talked about equivalent clean air from high level filtration. Okay, those are we have to do something, and there has to be something that we can do about it. And those are two things we can do. And basically, improve filtration or increase dilution, all right? And so one of the things that I like to point out to all of you when we're doing that is that there are ways to increase the outdoor air during periods of when we're in like a pandemic like COVID. Okay, like for instance, I went out every week during COVID, and knock on wood, I never got it. Okay, but I was always going to either buildings that had airside economizers because I knew they were bringing in a lot of outdoor air. Okay, or I went to places where restaurants and things like that where I could unzip the window because I knew the restaurant was going to run so negative I could suck in outside air and I'd sit right next to it. Okay, so I went out a lot during COVID, but I was careful when I went out because I kind of understood what was kind of going on. There are ways we can increase outdoor air. I mean, economizers or airside economizers are great, but also when we're in minimum mode, not economizing on a lot of these systems, we can look at the outdoor air conditions and the supply air conditions and basically increase the outdoor air. It just requires some instrumentation, okay? And then when you're making a claim for equivalent clean air, all right, you really better be measuring it, because you're doing equivalent clean air. You're making a claim that equivalent clean air is replacing your outdoor air. I don't know. I don't even want to say that's fine, but we'll just say that's fine. I'm not 100% on board with it, but that's okay. But if you're doing that, I think that you need to verify what your equivalent clean air is, and you have to measure it, okay? And so, standard 241, and it is supported by the EPA and CDC documents, as recent as November the 1st. So, it's something that you should be aware of, and the way to deal with this is you have to have a robust control strategy with the right instrumentation to go from your normal operating mode to your IRMM mode. Otherwise, it's not going to happen. Because that's what happened during COVID. You'd think we would have learned something. One of the biggest problems we had during COVID was we couldn't make changes to these systems because the control strategies weren't there to do it, and the instrumentation wasn't there to do it. And here we are, a few years into this thing, and we still haven't made these systems work. And they can, okay? For instance, when we're doing, we're doing DCV, right? That's what this is about. Both the CDC recommends disabling DCV. Recommended it during COVID. Disable it. Well, how do you do that? Okay? A lot of the DCV systems that were in place were just two arbitrary set points, a min-min and a min-max, and you throttle between a min-min and a min-max to keep your CO2 set point. So when you said, well, I'm going to disable it, I'll go to the min-max, well, there's a good chance you were overventilating and couldn't condition it, had pressurization problems and everything else, okay? You have to have a strategy that allows you to disable it. If you think back to the strategies I talked to you about, that use airflow measurement either as limit control or as part of this overall strategy, you would just override the set point. You'd override the set point. You'd say, I'm not doing DCV, and boom, I'm going to maintain, design outdoor air. And if you were even a little bit more advanced in your thinking about what you were measuring, you might say, oh, I'm in an off-peak load condition. I can increase it even more as long as I have the ability to exhaust it and not create pressurization problems. Okay? We have the capability of making these buildings work. We have the technology, we have the smarts, we have the instrumentation, we have everything, but we're not doing it. Okay? And if you don't think something like this is going to happen again, I think you're naive. Something like this is going to happen again. Do we want to go through the last few years again? That's ridiculous. Let's make these buildings smarter and let's make these buildings better. But to do that, everything can't be energy, 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 energy. And everything can't be cheap, 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 cheap. You know, it's got to be, we've got to make these systems work, and we got to be able to adapt to the conditions. And I really feel strongly about that. And that's probably the reason I still do this. Okay? Now, I'm going to come back again, and we're going to talk a little bit about technology, all right? And so, you know, it's good for me to just kind of walk off here and reset my brain after this DCV talk. We'll come back and talk about technology, and then we'll finish up with some strategies, all right? So I'll see you in a sec, and I'll be back on this in a few. Thanks. There you are.
Oh yeah. Hey.
Yeah. Hey.
How's it going?
Oh, well, it's going. I see
Not
where.
good or bad?
Well, I don't know, but I see where you've been.
Well,
At least you brought.
I did bring you a glass of
At least you
wine.
brought me a glass of wine.
Yeah.
So you know, how's it going?
It's going good.
Yeah. Cheers.
Yeah, cheers.
Yeah. All right, everybody. Well, we're gonna, you know, once again, we're back here for a little bit of a break, and anyhow, we're gonna
I don't know what that was for.
Well, I don't know either. Anyhow, you know, the way things are going, I'm pretty sure I can get another break in. So I'm gonna do the same thing I did last time. You know, after we kind of go, and I may go back for a couple minutes where she was.
It's pretty nice over there.
And
It's a lot warmer.
yeah, and you know, I'll put the Morgan clock back on, and so, you know, we'll give you a few more minutes, and then, which I actually have to go back, and before we can go there, you gotta follow me back here, because I gotta go put on the Morgan clock before they can before we can go there.
Okay.
All right, so you know, we'll see how this all works out. So, at any rate, again, I don't think you want to listen to me. You're already doing that. So, we'll see you. I'm pretty sure I can get one more break in. Maybe you can bring those holiday hats this time.
Oh.
Yeah, why not?
All right. You insist.
You know, I think we brought them here.
I know, still. I don't like the holiday hat, but I'll wear it.
She doesn't like it because she says
Messes
it
up my hair.
messes up her hair. But wait till you see what I look like. All right. So anyhow, we'll be right back. Okay.
See you guys.
Thanks.
Okay, we're halfway through our break. 5 minutes left, so probably time to think about starting to finish up whatever it is that you were doing. Okay, we're down to 2 minutes left, so we're going to get this thing started again in 2 minutes. If you do have any questions once this is done, you can either give me a call or send me an email, and I'll get back to you. Thanks. Okay, break is over. It's time to settle back down and so we can get this thing started again.
Okay, so now we're going to talk about technology. I'm going to primarily talk about EBTRON. Why not? But basically, you have a lot of choices out there with airflow measurement. I have people ask me all the time, why should I buy your stuff? Sometimes it's more money than the alternatives, and why should I do it? It's like, well, it works. That's a good starting point. Okay, it works. And if you're going to go through the effort of doing this, again, go back and think about the cost of the building and the cost of you can bring it all the way down. Look at everything as square foot costs. That's the way you should do it. You should not say, I do this with dampers all the time. If you have a bad control damper, it's not going to, your system's not going to work. And you can look at a good control damper to a bad control damper, and the price difference could be easily 2 times. All right. But if it doesn't work, what good is it? All right. You need the good control damper. Well, the same thing's true with the flow meter. All right. And when you look at the square foot cost, that's a good way to look at it, is what does it cost per square foot of floor area? What's it adding to the cost of the building? And what are you saving as a cost of the building by removing it? And it's pretty small. Okay. And so now, so to me, it's like, make these systems work, choose the best solution. We've been doing this since 1983. I've been personally doing this since 1984. I work with Mike Urbaniak. We've been designing this stuff together since 1984. Got a good team, people that have been around a long time at EBTRON. I always say to people, it's like the Roach Motel. Once you check in, you don't check out of EBTRON. So we have a lot of experience, all right? In the 1980s, I mentioned Dave Solberg earlier, that he wrote that first paper for us. He came in, and we weren't HVAC people. He came in and taught us quite a bit about, systems. And, basically, we knew that in 1989, ASHRAE was going to do some major changes to Standard 62. So we positioned ourselves to make an airflow meter that can measure airflow rates in low flow, close coupled applications. And we came up with the control strategies to do it. We used this advanced thermal dispersion airflow measurement technique that we've used it for over 40 years. And, we have a very good manufacturing facility, and we got great people. That's why I always say to people, come to Bring a Guest. Bring a Guest in Myrtle Beach. You'll really get a handle on what we're all about, but we really are a measurable difference, okay? So, thermal. What makes thermal really a good choice for most of our HVAC applications? Well, when you're doing sensor design, okay, and you're selecting sensors, I learned this a long time ago, that if you have something that changes with what you're trying to measure, changes its signal with what you're trying to measure, you can probably make it into an instrument. Okay, and so what we want is, because we're in the microprocessor world where we're pushing and shoving numbers, we don't care if the raw signal is linear, okay? In fact, we don't even want it to be linear, okay? We want something where when we get to the more difficult flows to measure, we have more and more change in signal. And that's exactly what happens with thermal. The sensitivity increases as the velocity decreases. And that makes it great for using on outdoor air intakes and other HVAC applications. It's not the technology I would put on a jet airplane to measure airspeed, okay, but it is one that I would use in HVAC. When you compare that to differential pressure, whether it be pitot tube arrays or air wings, piezo rings, maybe we're not really using them so much for outdoor air, but we are using them. And some people do use them because they do some differential flow calculations that don't work. But all these Delta P devices, they have a problem that their sensitivity decreases. And actually on top of that, the pressure transducers that we use today for measuring airflow, the accuracy of those pressure transducers are a percentage of full scale, not a percentage of reading. So when you couple that with this kind of square root relationship, which looks like a square relationship here because I have the axes is reversed from the way that you would actually calculate it, but you find that differential pressure devices, the accuracy varies with the square of the turn down. So if you go 4-to-1 turn down on flow, you have 16 times less accuracy. So that's not a good solution. And vortex shedding is still out there. You really wouldn't want to use that on outside air. They have a linear signal. That was a great thing to do in the early 80s. But today it doesn't really matter, and the signal kind of drops off under 300 or 400 feet per minute. So it's not something that you necessarily want to use for outside air. Okay, so you compare the three and you're like, okay, thermal dispersion, and I'm not going to get into the EBTRON versus others today because I just don't feel like it. But there is a big difference between them, okay? Basically our technology, this is a lot of slide to absorb. Maybe I should put some animations in it, but, I'm just looking at speed here. If you look in the middle kind of the screen, the way an EBTRON works, we have two thermistors at each sensor node. It doesn't matter what product you're buying from us, they're all kind of doing this the same way. And we have one thermistor that we self-heat by passing a constant current through it. And we have another thermistor that we pass microamps of current through so it doesn't heat. And the self-heated one, we can measure the power dissipated to the airstream. We can measure its body temperature. The zero power we're using to measure the ambient air temperature. We've been doing it this way for over 40 years. Okay, so it's how we do flow. That relationship, power and delta T, and a few other things is proportional to the velocity or the mass velocity, however you want to look at it. Okay, so that's how it works. The basic principle of operation. We do a lot of things part of it's from going to the College of Hard Knocks, I guess. Our sensors all have to be able to withstand heavy salt bath evaporation test. They have to be able to withstand being hung over fuming acid baths. And the reason for that is not that those are our sensor nodes. They're not going to read right when they look like that, okay? We clean them up, make sure they still function as they did when they were put into the baths. The reason is, particularly in outdoor air intakes are dirty, okay? And you got salt and you've got atmospheric acids and sulfur dioxide, things like that really can create problems after year of exposure. And so we sent this out to some independent lab to verify our test results and just say, hey, these things are not affected by salt or atmospheric acids or even stronger acids. It doesn't mean that airflow meters in some applications won't get fouled up. We're not going to get into that a whole lot, but it's not an EBTRON thing. It's anything in an outdoor air intake. I mean, if your outdoor air intake is dirty, okay, everything's going to get covered and it is going to affect its reading, and you should really think about pre-filtering it, okay? And I think I'm going to get back to offering some washable filters for people that are in dirty environments, but it's not an EBTRON thing, it's an everybody thing, okay? And so, but for the most part, it's not necessarily the case. I do want to say to some of you out there, dirty doesn't mean you have to clean it. I've got flow meters at EBTRON that I can show you in the outside air intake, 20 years old, that look awful, that still read the same as they used to. But this test is to make sure that when they're exposed to salt or they're exposed to atmospheric acids, they don't fall apart, okay? And, we have to calibrate them. So who do we calibrate to? Well, we don't even go to a third-party lab. We go directly to NIST in Gaithersburg, Maryland. Okay, and we go up there and we actually accompany our standard, and we do basically a report on calibration. We come back, we transfer that to our calibration tunnels. The thermistors, that's the bottom left there. You can't see it, but you can get a copy of that report. The top right is just an aging study we do on thermistors. Do they drift? Do they not drift? They do not drift. We use a very solid thermistor. It's oven aged and stabilized. Very, very stable part, so you got long-term stability of the part. We come back, we have these calibration tunnels. We'll show you if you come to the factory. Each individual sensor is calibrated individually. Each individual, calibrated individually at multiple points. This is like our Gold Series probes. We calibrate them between 0 and 5,000 feet per minute. It's a 16-point calibration. That's how we end up with a percent of reading device. Okay. With the transmitter, so basically what ends up happening is each one of these sensor nodes gets calibrated in these tunnels. And if we do a report of calibration, which is what you see there on the left, on an individual sensor node, they're all well sub 1% of reading over the entire range, okay? And, that's why our sensor node accuracy is 2% of reading, okay? And what we're doing with the transmitter, so when you go, what we have now is we just pick a probe there and a transmitter. All the calibration data is stored in a serial memory chip in the cable connector. Okay, so they're plug and play. Okay, they don't have to be matched, even though they're all very different. And you plug them into the transmitter. All that calibration data gets transferred over. And what the transmitter is, it's kind of not really the right word for it. It's a microcomputer, a high performance multi-channel voltmeter with current sources. Okay, everything in our transmitter that we do is industrial integrated circuits and industrial components, so they're very low drift with changes in temperature. Okay, and so the transmitter is basically reversing the calibration process. So the first thing it has to do is it basically has to multiplex in all the voltages from the sensors, convert them to binary with an A to D converter, so that's the voltage measurement part, and then we push and shove numbers, and we calculate, temperature is part of our calculation of airflow, so we calculate temperature and airflow, and then we average both and send them out. We provide velocity weighted temperature, we provide basically, enthalpy if you want it. It's a lot of good things that we have with the EBTRON, not just a flow meter. From a connectivity perspective, we've got you covered. We have linear analog outputs. We have RS-45, which is field selectable between BACnet and Modbus. Ethernet, same thing, BACnet and Modbus. We have LAN. We even have a data logger output card that has a thumb drive that goes in it for logging. We pretty much have you covered here. Quickly, the reason I say quickly is I feel like our reps have probably explained the product lines to you, but I'll just do it quickly. Our highest sensor density products are our Gold Series. That means they have more sensors than any other product we make. Our Gold Series on our P probes is the things that we put in the ducts. We put them in the outside air intakes or anywhere we want to measure airflow rates. Okay. We have a primary sensor density. We call it a seed sensor density. We have another one that's a plus. They're both the same number of sensing points per area. Okay. We're probably going to re-release some lower sensor density options, particularly for this DCV limit control. I think that I can make an argument that you can go with a slightly lesser flow meter on some DCV applications rather than not do anything, okay? We have something we call the hybrid, which is our most economical, lowest sensor density product for larger openings and ducts and intakes. keep in mind it only has 4 sensors in it. Sensing nodes basically equates to what is your uncertainty, okay? It's not that you can't have a 4 sensor unit and a 16 sensor unit that provide you with the same accuracy. But the probability is that the one with the more sensors is going to be more accurate. And a lot of our applications require that kind of accuracy, okay? Outdoor air intakes, particularly close coupled outdoor air intakes where you have a louver and a hood and a damper, you really have to put in the high sensor density flow measurement to get good accuracy because you don't have any room, okay? You have tremendous velocity profiles and very difficult to get good measurements. So those are the products for what I would say is our larger duct plenums outside air intakes, okay? We do make an application specific line. We call it the EBFlow product line, okay? The EBFlow product line is kind of application specific. So, you know, if you have like a 6-ton rooftop unit, it may not make any sense from a cost perspective to put in an EBTRON Gold Series or hybrid. It just doesn't make sense. But the EFX 2000-U, which is just a couple sensing points, same technology, is probably a good choice for you on some of these smaller rooftop units. It's also a good choice for you on a lot of energy recovery type units, particularly desiccant wheel units where the desiccant wheel itself acts as a flow straightener. We can get by with less points, okay? We get into terminal box size stuff. It's not necessarily that you're doing it for a VAV system. It might be a DOAS ventilation zone, okay? You know, we have our EFX 2000-T, which is basically a small probe and a kind of cut back transmitter, okay? We even have a version that the lowest cost device we make is the EF-X1000-T. And that's basically the electronics is on the end of the probe, okay? And that's the lowest cost thing that we can provide you with, okay? At any rate, these are the products that we have for flow measurement, and so we have a pretty much have you covered. When we get into fan inlet measurement, we have products that are designed for, you know, single and dual inlet fans as well as fan arrays. We can show you all the test data you want to show you that our fan array devices don't affect fan performance, okay? Not going to do it today, but it's a fan array product, okay? We've just released our IAQ enforcer system. If you're an old-time EBTRON customer, you would remember back in the 90s we made something called the IAQ enforcer. The IAQ enforcer basically had a lot of probes that were, the electronics were on the end of the probe, and we daisy chained it back to a single panel. You know, technology has really improved over the years, so we kind of kept the name and have a very similar type of an idea, but it's not not the same as it was in the 90s, okay? We decided to come up with basically a tablet style touchscreen that's application driven. The application driven concept for us is a really big deal because we see a lot of people making displays and things like that, but the way that they're making these displays is they're very specific to function, okay? And we're like, we don't want that. We want to be application based so that over time we can add and modify applications, things outside of just being able to display or configure a device. So this is available now, all right? So we have, I don't want to confuse people because you hear me say something and I'm not saying what and then you hear me say something else. The first version that we have released here is an Ethernet version. It talks to all of the EBTRON products that are connected to it via Ethernet over just basically a Cat5e or higher cable, typically going back to it, you know, each unit goes back to an Ethernet switch. We did that because Cat5e cable is cheap, okay? We're not expecting you to use that. In fact, this configuration doesn't want you to use that Ethernet connection to your building automation system. What you want to use from our device is the analog outputs back to your building automation system from each individual transmitter, just like you do it today. We are in the process of releasing an additional card that's an Ethernet RS-45 card for those of you that either want to talk to the transmitters via analog or RS-45. The follow-up to that is an Ethernet card, which either allows you to set up your own Ethernet network for your building automation system, and or you use it can be configured as an industrial Ethernet switch, so you daisy chain the units together. Too much to talk about in this one slide or two slides that I'm going to show you, but I think it is a really good product that's going to do a lot for you, okay? And then you can look at this and say, well, gee, how much is it? And I will tell you, if you can locate, if you're in a mechanical room, okay, and you can eliminate extension cables, like 20 or 30 foot extension cables on 2 locations in that mechanical room, you paid for this device. So honestly, it shouldn't even be an ad, okay? Right now it's coming out with 4 standard installed applications. Those will increase over time. One of them's a display app, one of them's a device configuration app, so that's important. Display shows everything that's connected to it, up to 16 different transmitters, okay? Device configuration app allows you to configure each one of those, from this panel. The device summary app is just something that shows you everything that's connected. The EBLink reader app is basically our phone app, but it's on this device. We're adding to those. In terms of the display app, I'm showing a display app here, for instance, on a Gold Series unit. Gold Series transmitter is basically 5 sensors. It could be as much as 5 sensors. So you got airflow, you got temperature, and if you added the relative humidity sensor, you got RH, you got dew point, you got enthalpy. That does not count as, that's a single device, okay? So it'll display that way. And it'll scroll through all these devices. We're working on other applications, more than I am showing you here. This has to do with the IAQ DCV applications. Field Match Wizard is designed so that when you have devices in marginal locations, you can adjust one to match the other. It does it automatically, okay? We've been able to get flow meters within 0.5% of each other by doing that. The fan array monitor is just that. It's, some people want to look at the individual fans, so we're working on that. The other ones are a little further out. They're going to work with some of our Green Troll products that measure CO2 and other air quality parameters. Multi-zone DCV ventilation calculator is probably the longest one out there. That one to me really requires good counting. Okay, but there's other devices, and the way that you get these devices, these applications, is that you go to EBTRON.com, and we basically have a page for downloads and updates, so new apps and updates, and you download them to a thumb drive, and then you connect a thumb drive to USB port on this display, and that's how there's no internet connection required. Okay, so I think that's some real positive product stuff for us. And like I say, I think we're still, I think we're, after 41 years, I think we're still the better mousetrap. We still have the best technology. We have a good solid 3-year warranty, something we call advanced replacement. We think if there's a warranty problem, we'll send you something out before we get it back from you. Local representation, I think you should all realize how important that is. And then when you call us, you get a person on the phone, which I think is nice. Okay, so the next thing to do, which is going to finish this thing up, is control strategies. And in the control strategy side of this, we're not actually going to get into sequences just because of time, but we could. All right, so that's what I'm going to do. when I come back from my little short break here again. All right? Thank you. All right. Well, got another break in. There's only one problem with this picture, but anyhow, we'll see how this goes. I can't imagine that she can be too far behind me. So as soon as we get a chance, what we're going to do now is we're just going to go in. We're gonna finish this up, and then hopefully a lot of you join us on the GoToMeeting link, and with Kevin, we'll be here somewhere through here. He's setting up someplace, and so that'll work. Oh yeah,
Hey.
It's nice of you to show up.
Well, I brought you things
Yeah.
and gifts, and I put on my holiday hat as you asked.
Okay, here, take
It's right
that.
back, okay? Let's see how this goes. Oh. I don't know. You gotta fix the hat tape. Like fix the little ball. Like
Am I supposed to do
I don't know. Okay, let's just.
Is that what it's supposed to look like?
I don't know. It looks kind of funky if you don't have that part because it looks like you just got on like the ski hat thing. But
It's okay.
Okay.
It's all right. Yeah.
good,
Yeah.
good. So this has been going good for you today.
And so
Thank you.
far, so good. Hey, this one's pretty good.
Yeah.
They're all pretty good here, but
They are.
there's some that I like
I've,
better than others. So
Tasted a few.
anyhow, we have an unfair advantage over you folks. We have more to choose from. But anyhow, like I said, we should be able to finish this up. Should be right on time, maybe even a little early, and that'll give you some time to get yourself settled in. 1/4 the hour, so depending on where you're at in the country is when we're going to do this. Kevin usually stays on 45 minutes to an hour. I said it earlier, but I'll say it again. This is a good opportunity. He's really, really sharp. Use the chat to ask if you have any questions at all, because he'll answer questions about just about anything that has to do with wine and winemaking. And then let me think if there's anything else. Oh yeah. When you do come on, so we're using GoToMeeting because at the end you can turn on your cameras and you can turn on your microphone, and those of you that want to engage and have a discussion about things that probably won't be like this presentation, because by that time I don't think I'm going to be in any position to talk technical, but I'm not driving anywhere. I'm not. Okay.
No, okay.
We're actually staying here tonight, which is nice. But it's a good time for you to ask questions, stuff like that. But as a reminder, please do not. And not everybody listens on this, because I don't think everybody's listening. But do not turn on your microphone or your camera until Kevin's done. We let Kevin talk, and then at the end you can put on your microphone and your camera. And if you have questions, use the chat to ask him questions. He's sitting there and reading the chat bars. Okay, so I guess that's about it. Let me go finish this up, and then I guess the next time I'll actually see y'all is on the GoToMeeting side of it. Okay, see you where I'm talking kind of like this. Okay, so all right, I'm ready. Yeah, and I just assume just get this done. Okay.
Cheers.
Yeah, cheers.
At least you didn't jerk the damn hat off my head this time.
Okay, now we're going to talk about control strategies. But before we do, I was actually reminded during the break that I left out a very important slide. on DCV, so I'm going to do it first before we go into control strategies, okay? So, I just want to remind everybody that outdoor air is required to dilute contaminants. Don't forget that. And that CO2 is generally not a contaminant. It's not that it can't be, it generally is not. And Standard 62 has recognized this for a long time, but I want to make sure that I point it out because I have seen some companies that are saying, hey, we can significantly reduce your outdoor air, with our air cleaning. And the reason they're saying that is their air cleaning is removing CO2, so the CO2 levels are low, and then they do CO2 DCV, okay, and that's not allowed, okay, and it's not, not everybody understands why, because so many people think that CO2 is the air quality measurement, all right, so I should have put this slide in way back, but I'm putting it in now. So when we look at what Standard 62 says, under DCV, especially with the new addendum AB approval, it says CO2 sensors shall be permitted to be used for DCV in accordance with the following subsections. And we're not going to do those right now, but we're just going to say right underneath it there's an exception, okay, and it says CO2-based DCV shall not be applied in zones with indoor sources of CO2 other than occupants, because you're using CO2 as a proxy, okay? Or with CO2 removal mechanisms such as gaseous air cleaners. And one of the things that I'm showing you on the right there, even though the graph is kind of small, is that I told you that, dynamic model I can put in CO2 removal. So in this case, I'm removing a certain percentage of CO2 per pass over this air cleaner. And I'm still doing DCV. So when you look at that slide, you're like, okay, again, the red and the green is associated with the left axis and is the amount of outdoor air you need to dilute the contaminants in the space, okay? And that the axis on the right goes with the blue, which is the CO2 level. And here we've removed the CO2, we're controlling to it. The CO2 is right at 1,000 parts per million, and everybody feels good about it, but you've significantly reduced the amount of outdoor air that you're bringing in, maybe 70 or 80%, and people feel good about that. They're like, well, I saved energy. It's like, yeah, but you needed the outdoor air for dilution. You don't understand the relationship between CO2 and ventilation. You don't know why you're controlling CO2 levels. So, it's just something to think about. That's why CO2 DCV is not part of the IAQP. It shouldn't be part of the IAQP, and that's why. All right, so now we're going to just go where I should have gone, which is we're back to control strategies, right? So, every now and then I leave something out. So anyhow, normally when I do these strategies, I talk about figuring out what the difference between the flow rates need to be for pressurization, and then, what does the outside air set point need to be. Today I'm just going to talk about the outside air set point. The strategies I'm going to show you are all airflow control for pressurization. You could substitute in static pressure. The problem I have when you do static pressure control of space is you really don't know how much air you have, so it's easy in DCV to end up with pressurization problems because you fell below, you don't have enough air, okay, to make up for exhaust and pressurization. So I'm going to show it as an all airflow strategy. I'm not going to get into as much detail as you may want. I really need to just write these things out. I'm going to start based on design occupancy, which means we're not doing DCV because why not, right? So this is fixed set point, maybe office spaces. And basically what we're typically doing there is we're determining the ventilation rate required by code. It's typically based on the ventilation rate procedure standard 62, unless you're in California. Some of you make claims using the IAQP to reduce outdoor air. just remember you're taking on the liability to do that. You're using some kind of air cleaning, but that's completely up to you if you want to do that. Okay, some of you are using equivalent clean air. There's different ways you're coming up with this. The one thing that I find that gets ignored a lot is determine the outdoor air required for pressurization. And most folks talk about it as, when they do understand it and recognize it, they say, well, you have to have at least as much for the local exhaust. Yeah, that's true, but you need a little bit more than that if you're trying to go positive, because first of all, you don't want to have, there's no such thing as zero tolerance, so there's some error in your measurements, right? You could think you're positive and be a little negative. And so you always want to have a little bit of extra air to pressurize space. The tighter the spaces get, the smaller this QP or pressurization flow is. The smaller it gets, the harder it is going to be to control buildings, by the way. And then you just choose the greater of A or B as your outside air set point. I mean, it's typically driven, minimum outdoor air is typically driven by the occupant load, but it doesn't have to be, okay? And if you have more outdoor air for the occupant load for dilution than you need for pressurization, you need to be relieving or exhausting some of that air. On the CO2, based on CO2 levels or actual occupancy, so just DCV in general, that's really what we're here talking about. What you need to do here is you need to determine ventilation rate required by code for the maximum expected population. And you really are working through the VRP here, okay, because DCV is not permitted under the IAQP. So don't make that mistake. Remember, we talked about that earlier, that when you reduce the outdoor air because they're codependent with CO2, you're essentially raising the CO2 level of the space. And so that the only way you'll meet your CO2 levels is to provide more air than you designed your system to ventilate. So you got to be really careful with that. But anyhow, do it based on the maximum expected population. And then again, look at how much outdoor air do you need for pressurization, okay? And look at the minimum amount of outdoor air you need. So, a lot of times people do DCV and they don't think about that either. It's like, okay, yeah, I'll let it go down to, basically unoccupied, nobody, but still in occupied mode. But hey, your local exhaust might be greater than that. And when you let DCV fall too low, you end up with pressurization problems. And pressurization problems, again, if you go negative, you're bringing whatever's outdoors indoors. And in moist climates, a huge problem. But even in all climates, you're bringing in untreated outdoor air, dirt, dust, whatever else is outside. And so it's choose the greater of B and C. That's your kind of low limit. It's not always clear. People don't always see that, but it is the way it should be done, okay? So now we're just going to go quickly through, these strategies. They're really difficult to do in a webinar, okay? Because there's a lot going on the screen, all right? So, if we have a recirculating air handling system with a supply and return fan, we're typically controlling building pressure by controlling the return fan to keep a flow differential. You may be doing it to maintain space static pressure. We can argue about what's better or worse at another time, okay? I like flows because when you do flows, you know that you've provided enough airflow for the outside air. And then typically in a recirculating unit, we're going to be, with DCV, we're going to be modulating the outside air and the recirculation air dampers, preferably in sequence to maintain that outside air set point. So we're resetting the outside air set point. We've already talked about how the logic is for determining that, okay? And so that's what we've got going on. Don't forget about the toilet exhausts. You may not measure. Typically, you don't measure toilet exhaust. There's a number of reasons why you don't do that. Air balance is good. Go on fan status. But the bottom line is this is kind of what you got to do there. Supply fan with a relief fan in a recirculating unit at the unit, it's really the same thing. Okay, we typically control that differential flow between the supply and the return flow rates, even though it's a relief fan, and then we're sequencing those dampers to maintain the outside air set point. To me, there's really no difference in these units. And this is where measuring flows is nice, because if you're not measuring flows, supply relief fan systems could actually take outside air and blow it back out of the building. That doesn't happen when you're doing airflow control. Okay, if you have a separate relief system, sometimes they're a little harder to handle the pressurization because your measurement points aren't as good, but in terms of controlling the outside air, it's the same thing. We're going to be sequencing these dampers to maintain whatever the outside air set point is during DCV. All right. Hey, maybe we have makeup air units. I kind of like get twofer. I get a twofer here on this. We're either doing multiple air handlers, or we could be fan coils. It could be, it could be big air handlers on floors, or it could be VRF with fan coils or something else like that. We have a makeup air unit. We want to get, control. We want to get good measurement at the unit. Okay. And typically in these applications, that's our like EF series product, so it's pretty cost effective, okay, because it's smaller units. So you should definitely look into that, particularly with fan coils and variable speed and DCV and all these different things you got going on there. But it's not just recirculating air handlers, and it's DOAS, and particularly DOAS with DCV, which is what I'm really talking about here. So ASHRAE's design guide for dedicated outdoor air systems has a couple bullets we pulled out, basically talks about, if you think about, sort of reading this to you, if you think about this, when you're doing multi-zone DOAS, it's very much like multi-zone VAV. Multi-zone VAV, you're varying your VAV boxes for thermal reasons, load in the space, thermal load in the space for temperature control. And so you might think, but it's not a good idea to try to do VAV without airflow measurement at the box, right? So you reset the airflow set point between min and max at the box. And it's because the pressures are varying in the system. And, that's the only way you can hold the flows within the range that you want them. The same thing's true for DOAS, except in DOAS, you're not doing multi-zone DOAS for temperature control, you're doing it for ventilation, for air quality, but it's the same exact thing. So you want to be measuring and controlling airflow rates at the zone. You certainly can't depend on damper position, as one zone changes differently than another. And so we're going to just start with simple, though. If it's a single zone I just think gets ignored a lot, particularly when folks are doing, single zone DOAS, energy recovery, maybe this is, and I've seen so many cases, where they throttle back the outside air, they don't pay that much attention to the exhaust air, and the space goes negative, and the next thing you know, you have plenty of outdoor air, but your walls are sweating, and it's because you got a pressurization problem. So even though we're not really talking pressurization, I actually am in a way here. So we want to have the flow station measuring the total outside airflow path, doing what we talked about for resetting the airflow set point, but then even as important is tracking that exhaust side to make sure you don't have a pressurization problem. When you get into multi-zone, this is what I was saying a couple slides back. The bare minimum that you should be doing, okay, is you should be measuring the airflow into that zone and resetting your airflow rate between a min and max, as we discussed previously, based on either the CO2 level or if you've measured the occupancy. Okay, in this slide here, some people want to have a little redundancy and put this total outside air in the DOAS unit. I don't think you really necessarily have to do that if you're using EBTRONs, but I put it in here anyhow. I think this slide here is what I would do with EBTRONs. I would just sum the EBTRONs because they're accurate enough to do that, all right, on the supply side. It's just up to you how you want to do it. But this still can end up with individual ventilation zone pressurization problems. So it all depends on where you're at. Drier climates, I think you can kind of get away with this. The other thing I want to make sure I point out is if you have toilet exhausts that are affecting these pressure zones, you have to take that into consideration for what your differential needs to be. I mean, there's air leaving. If that air is leaving affects those ventilation zones, you need to take that into account, okay? When you get into really moist climates, this might look like overkill, but it really isn't. You want to do the outside air control like we talked about, but you want to also track each ventilation zone, because you don't want to be in a really particularly moist climate. You don't want to be in a moist climate where you end up with a pressure zone that's negative. I mean, it's like, I've seen people say, oh, well, as long as the building as a whole is okay. Well, that's kind of bull. The building as a whole can be okay, but a ventilation zone can be negative. If a ventilation zone is negative, you can have a moisture problem and a mold problem. So I don't necessarily agree with that. So you kind of do a little tracking deal here too. Okay. I have a note here which does somewhat complicate this. Only if you have toilet exhausts that are affecting this is you have to add additional logic to make sure that the total outside air that you're providing to those ventilation zones never goes below the pressurization, the sum of the pressurization requirements for all the zones, plus that toilet exhaust. Otherwise, you're going to end up with pressurization problems. Okay? Believe it or not, we have come to the end. So I think that I feel good about coming to the end. I'm sure you feel good about coming to the end. So if you're going to join us, with Kevin, for the wine tasting, you get out of GoTo webinar, which is what you're in, and you get into GoToMeeting, which is a separate link. And the reason we do that is because we feel like GoToMeeting is a little more interactive. You can all show your faces if you want. You probably can't all show your faces, but we have a limit to how many faces we can show, right? But it's just a more interactive way. I think it works better for Kevin in the way that he's going to do his presentation. I do want to say to you, when you get on, and it's amazing to me that nobody's listening to me on this, but when you get on, not nobody, a lot of people aren't, you want to turn your camera off and your microphone off, because initially we're giving all the control over to Kevin, and he's going to talk for about 45 minutes. I call him Professor Kevin. He really knows what he's talking about. You'll learn a lot. Use the chat to ask him questions. He's great at answering the questions. When we get done with it, okay, when he gets off, you can, if you want, you can turn your camera on and you can turn your microphone on and we can have a conversation about anything you want. But by that time, generally speaking, we're all done working. Okay, so thanks again. If you have any questions, Ask David, engineeredsalescorp.com works. It goes to me, it goes to Josh, so it gets, we'll get answered. Don't forget about your wine glass counts, okay? You have to get those wine glass counts in by the 15 after the hour if you want to be considered for the case of wine I'm going to ship the winner. And just a reminder, there's going to be probably a lot of you that get the wine glass counts right. So of the people that do, we're going to just pull out of the hat tomorrow Okay, and we're going to contact everybody who responded and say, here's who won, and thanks for participating. All right. I will see you shortly, hopefully. Take care.